Okay, so we're going to continue our discussion on vectors. First thing we are going to talk about is the dot product. Okay. If we have two vectors, vector u and vector v, then their dot product is the sum of the product of the horizontal components and the product of the vertical components. Okay, here are our two vectors. The dot product, we are going to simply take 2 times 3 and add it to -1 times -2, which is
8.
Thanks. That is the dot product. You remember that now?
We're going to have to graph those.
Okay, so here's the deal about a dot product. A dot product is a scalar. It is
Okay.
not a vector. Okay.
So is it
So
the
no.
scalar v times v?
What?
Is it like the scalar v times v?
Yeah. The cross product is how we take a product of two vectors and get a vector. And we will do that when we're all done with our AP material. All right, so let's talk about some properties. The dot product is commutative. Yay. The dot product is distributive. Okay, we treat the dot product as multiplication. So if we have a scalar times a dot product, okay, that's all multiplication. So this would be the same thing as if we took the scalar times u and then did that dot product with v, or u times cv. Okay. Remember, we don't distribute if we have multiplication inside. We do one multiplication at a time. Okay. If we take the dot product of u, any vector, and the zero vector, what are we going to get?
0.
0. So do you see how I kind of bolded 0? That's the zero vector, 0, 0.
What if the u vector is infinity?
Not possible.
Ah, okay.
Wait, so possibly have
The vector graphs that trend towards
a vector of infinity, infinity?
You cannot have an infinite vector. It has to have magnitude and derivative. Magnitude is finite.
Ah, okay.
Yes. What'd you say?
This is just starting to there.
I'll make it make sense. Done.
Okay. V dot V is the same thing as the magnitude squared. You take the dot product of a vector and itself. Okay. Let's imagine that's doing that. If we take the dot product of V and V, okay, we're taking the vertical components and multiplying them and adding it to the horizontal components and multiplying them. That's what's under the square root in our magnitude. So magnitude squared. Okay. All right. These, I mean, it's important to know for order of operations, but I wouldn't say you're going to use these often. Okay. Let's talk about if we have vector u and vector v, is it possible for us to find that angle in between? Yes, yes it is. Okay. If you recall from pre-calculus, this formula is derived from the law of cosines. Okay, I'm not going to go through that proof, but that is what, how we get this. Okay.
You
Yes.
need to remember the law of cosine.
No, you need to remember that. Okay. Now, keep in mind that the inverse cosine range is 0 to pi. And so this will always give us an angle between either 0 and pi or 0 and 180. Okay, so it's always going to find the closest angle. So, like for example, if we had this as u and this as v, okay, it's not going to find this angle here. It's going to find that right there. Okay. So let's say that we have two vectors, 2, -3, and 1, -2. Is that the one that I gave you before? Okay. So we're going to need a dot product and each magnitude if we're going to find the angle in between. So, Tyler, what's the magnitude of, we're going to call this u?
Square root of 13.
Good. And we'll call this v. Gabby, what's the magnitude of v?
Square root of 5.
Good. All right, and then we need the dot product, u dot v. What do you got for us, Sean?
Wait, give me a minute, I'm still copying stuff down.
That's fine.
Eight.
Do you agree with Sean? I have one. Okay, 3 then. Okay. So the cosine of the angle in between those two is 8 over radical 13 radical 5. Okay, so to solve for theta, we can put in our calculator inverse cosine of this fraction. Okay, my advice to you would be to multiply that denominator, or remember that if you're dividing by more than one number, it has to be put in parentheses. I would be tempted though to call that radical 65 and just save some time, since 13 times 5 isn't a difficult number to calculate in your head.
Is there ever going to be an instance where we're given theta and u and we have to solve for v?
No. Not in this class.
You want,
I do. Define in degrees.
I wasn't sure if you wanted.
Degrees is fine. That's not you got it.
No, I think it was.
Okay.
Oh, 7.12 degrees.
Can we erase this question mark? Anyone want to confirm, Sean? Yeah. Okay. Sean, you seemed very uncertain.
No, I just didn't want to get it wrong.
Well, you could ask yourself, okay, if we have the vector 1, -2, and the vector 2, -3, does 7 degrees seem like a pretty reasonable angle?
It does now.
Okay. Thank you, Sean. All right. Now, what would happen if this 8 was instead a 0? The cosine of theta would equal 0. What does that mean?
The angle inside of 0 or no, 500.
Ah, 90 degrees. Okay. We call perpendicular vectors, do you remember the word for them? Orthogonal. Okay. Perpendicular vectors we call orthogonal. So if our dot product is 0, we know that the angle has to be 90 degrees, which means our vectors would be orthogonal. We don't have to go through the entire process of finding the angle. We know if that dot product is 0, our vectors are orthogonal. Makes sense? Okay. So, if I ask you, are these two vectors orthogonal? What would you say? Yes? And you would prove that to me. You wouldn't just write yes.
3 minus 3 equals 0.
You would say, well, their dot product is 2 times 3/2, which is 3, plus 18 times -1/6, which is -3. Their dot product is 0, therefore they are orthogonal. Okay. Ready for the fun stuff? So far, this has all been pre-calculus. In physics, you talk about projections.
Yes.
So first of all, V and W have to be non-zero vectors. Sounds kind of like a common sense thing, but we have to define it. The projection of V onto W is this. Write it down and then we're going to draw a picture.
It's basically a shadow, right?
Yes. It is a shadow.
Assuming that the sun is directly above it.
Okay? This red right here, this is the vector. That's the projection vector. Okay? Just as Josh explained it, that is exactly what I was going to say. It's like the shadow. So it's going in the same direction as W, first of all. But its length is different than B.
possible for W to be smaller than the projection of V onto W?
Is it possible?
For W to be smaller than the
Smaller.
projection? Like say,
Yeah, no, I know what you mean. I know what you mean. I'm thinking. I think it's okay if W is smaller.
would the projection be smaller?
The projection just go past it.
The projection would just go past W. Yeah, I think that would be fine. Mathematically, I don't see anything that would be a problem if that were the case. Okay. Now, let me kind of break this down for you. What is W over the magnitude of W? We've done that before. We've taken a vector and multiplied it by 1 over its magnitude. Unit vector. So that W over one of these, that is giving it in that direction of W. Okay? And then V dot W over magnitude of W. Okay? That's how we're getting it, the length of it. We need it. Okay? So let's work with an example so you can see this at work. Okay? V equals, oh, you know what? I have one more thing to define. I'm sorry. We need to talk about the decomposition of V. All right? Right now, I'm going to call V1 the projection of V onto W, just so I don't have to write that big projection thing every time. Okay? I'm going to draw a new picture. All right? Okay. So I'm going to call this is our projection vector. I just called it V1 because I don't want to write all of that up there. Okay? This right here is called V2. And what is true about V1 and V2? Okay, they're orthogonal and they have equal magnitude, yes. So how would I find that vector?
Put the coordinates. Wait, no.
Well, not necessarily. Okay. What I want you to think about is here's V. What green vector did I just draw? V1, but in reverse. So you would take V minus V1 to get that decomposition. Oh,
Wait, okay.
didn't mean to go that far.
What can we use the decomposition for?
I will show you here after I show you how. Oh, the decomposition? I'm gonna have to think about that. It's just there. Is that what you're saying? Yeah, it's just there.
You might as well learn how to find out.
Well, what's nice is it gives us an orthogonal to W. and the projection. Right now, I'm not coming up with anything physics-wise that would be helpful, but I am sure that there's something.
It's okay, we don't really need help.
We could take a field trip to Marshall's class.
We could do that.
We can just keep going.
We should do that instead of quiz.
So, the projection of V onto W. Okay, that's kind of how I like to write it. The projection of V onto W is the dot product. So, Sammy, what's the dot product of those two? 3. Over the magnitude of W squared. So, what is the magnitude of W, Josh N?
Square root of 2. Square. So 2.
Excellent. And then we're going to multiply this to W. So our projection vector is 3/2, 3/2.
And to deconstruct it.
So then if we want the vector orthogonal to both that and W, we would take 2, 1 and subtract 3/2, 3/2, and that would be 1/2, -1/2. There will be a question like this. Okay. All right. Now, what can we do with the projection vector?
Graph it.
Well, how is it useful in physics?
Same question.
So,
We did that.
sorry. That was misleading.
This place is buoyant source.
No GH.
There's gonna be a person standing on top of it, like, no, he's going to be sitting underneath it.
What's the question? Mr. Martian, Mr. Martian, block.
Are you reading this as I'm writing it?
Yes.
How many feet down ground stuff?
Hmm? That's enough. Okay. We have a boat on a ramp. We want it to stay put. Hmm?
No, it's just it's physics.
Well, yeah, I told you that.
Yeah. Friction would really be nice.
We would need friction to keep the boat from.
Here's my boat. Beautiful boat.
Have you ever seen the SpongeBob movie?
No.
It looks like a Krabby Patty card.
Have you ever been to a lake? How do you get the boat in the water?
By a rope.
You drop the trailer down into the water and then back the boat out of it.
Okay,
The boat's already floating in it.
correct. So this boat, I have it on wheels.
You have it on.
Because on a ramp, that would make sense,
Yes.
right?
Yes.
Okay.
But if
Are you asking us or telling us?
Well, he doesn't like that I put wheels.
Oh no, it is viable.
Okay. So, first of all, what kind of force does this boat have?
Normal force.
There would be normal force.
600 pounds down. That's
Down. So we have a force vector of, negative 60, 600 down. Right? Pounds. Remember, we like put pounds.
Oh, you're talking about the J as in like the J.
Like as in down. Like instead of me writing 0, comma, negative 600, I'm writing negative 600J. Is that okay? We have to be able to work with both
Is it
forms.
like the IV?
That's lowercase
He's like
j,
making,
not uppercase
he's
j.
like making jewels.
Oh, I'm sorry.
Yeah,
I'm sorry,
I
that was
completely
confusing.
thought that was the jewels.
Okay. So that is that. Okay. Then, what else do we have to consider?
Normal.
Well, we have this guy right here, right?
Uh,
We have the ramp.
Yes.
Okay.
Okay, so the vector you just created is.
I just created a unit vector. Why did I create a unit vector? Okay, we don't know what the force is, so I'm just going to create a unit vector, and then we're going to find the projection vector of the force onto V, so then we know what kind of force we need to stop the boat. Does that make sense?
We need to take into account the normal.
Wait, is that like the?
That's what
Wait,
I-
is
That,
the area
that would be,
just
I think
through
that
like
would
the
be
force?
a normal force act.
No, because the normal, because
then we put-
you
No,
go
no,
like
no,
with the
force is
ramp,
at an angle,
it
right?
needs to be perpendicular with the ramp.
Yeah.
Well, so like. is the
What
area
needs
just
to be
the-
perpendicular to the ramp?
Normal force.
And what do you mean by normal force?
Means
The force of the ramp pushing back on the boat.
So question, so
Someone
the
back
area
there.
just.
So is that like friction?
No, no, no,
that's
no,
what
no,
makes the
normal
boat
force is
move.
really like, I push on the ground, the ground pushes on me.
I know.
That makes the boat move because it's got a horizontal, because it's at an angle, it has a horizontal component. Just the gravity doesn't make it move because there's only a vertical component, so it can't move horizontally. Normal force makes it so that it can move horizontally. That's what makes it go down.
Okay. Well, as far as keeping the boat still, the boat has a force acting down.
Yes.
Okay. Because it is 600 pounds.
Yes.
We have the ramp, 30 degrees. Okay. So the projection of that force of the boat onto the ramp is going to give us what we need to counteract the boat. Don't think we need to take into account normal
But
force.
here's what I'm still confused about, so the area you most recently
Normal
drew,
force creates the
so
motion.
the arrow on the left, what is that? Is that the area behind the acting
I
force?
just want to go to the.
Okay, first of all, it's not productive if everybody's yelling at me at once.
What is V?
Pretty sure V is the ramp.
So you,
Yeah?
yeah, but what force does it have? Is that like representing the counteracting force of whatever's pulling it back?
V is just a unit vector in the direction of the ramp.
Yeah.
It's not a force, it's just a vector.
Okay. So when we find our projection vector, it's actually going to be like it'll create this triangle for your normal force vector.
Alright, I'm happy.
Does that make sense?
Yeah.
Okay.
Take a bow. Or whatever the female version of bow.
Curtsy. Okay.
Weird and.
So can we find the projection now?
Yep.
And we're all okay with why we're finding the projection?
Yep.
Okay. So the projection of our force onto V is, what do we need in our numerator? Dot product. So negative 300. have a blank stare for this. I got that. Because we take 0 times radical 3 over 2 plus, why don't I just write that out? We have, because we don't have a horizontal component here, so it's just 0 times radical 3 halves plus negative 600 times 1 half. Okay. Over which magnitude do we need to square? This one, right? This is the fourth. This is the vector we need magnitude for, correct? Yay. Okay, and then we're going to multiply it by whatever force we're projecting it onto. So radical 3 halves I plus 1 half j. Okay, so our projection vector of F onto V is 150I negative 150I positive negative minus 150 square root of 3. Oh, you're right. Okay, so that's our projection vector. What is the force required? How do we find the force? What do we have to do with this projection vector now?
We have to set it equal to 16.
Nope. We need its magnitude. Is that fun? That's fun. Okay. Let me take a glance at your assignment very quickly. Okay. One last problem, and then we are done. Ready?
Yes.
Okay. Force. Work. I mean work. Really find work. What did you say?
Two vectors, and it's like
Okay. So we have a force of 15 pounds pulling a wagon 30 feet at an angle of 30 degrees. Now this is like verbatim a problem.
Where's that from?
Horizontal.
Oh, okay.
I couldn't fit it. So I kind of scribbled a little bit.
That's what
This is really more of a pre-calc problem, but we might as well talk about it since we're on the physics kick here. We have a wagon. And it is being pulled with a force of 15 pounds at an angle of 30 degrees. Okay, so we have force times displacement. Okay, Tyler, will you say what you mentioned earlier?
said work will be a scalar because force and displacement are vectors.
Okay, force and displacement are both vectors. We're basically going to take the force vector times a displacement vector. Okay? So our force vector, we have 15 pounds of force, but in this direction, correct? So we have 15 pounds of force times cosine of 30I plus 15 sine of 30J. Okay? Remember, that's how we write our vectors. Magnitude times the cosine of the angle I plus magnitude times the sine of the angle J. So since our force is 15, that's our magnitude, and then 30 is our angle. Okay? And we're going to take that, and we're going to take the dot product of what is our displacement vector, Tyler?
30, 0.
Okay, so 30I plus 0J. Okay. And here we have a dot product. So essentially we have 15 radical 3/2 times 30 plus 15/2 times 0 for our dot product. So we have 225 radical 3 foot-pounds of work. It does not appear that you have a very long assignment. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 problems. Okay? And some of those are as simple as what's the dot product. Okay. So you have the rest of class to work on the assignment. Hopefully you can get a good chunk of it done. This is what you need to be good to go on for the quiz tomorrow. And I can answer questions before we take the quiz. We can take about 5 minutes to kind of like gather our thoughts tomorrow. Okay? You are going to need to be able to take the first and second derivative of a parametric equation. You are going to have to determine speed and distance traveled, so speed and arc length, right, of a parametric equation. Finding points, as in coordinates of horizontal and vertical tangency. Writing a vector given 2 points. Finding the magnitude of a vector. Writing the vector in both forms, so either with the chevrons in component form or the linear combination form. Okay. Taking maybe a word problem and essentially adding 2 vectors together to figure out the resulting force and magnitude, or magnitude and direction. You will have to find a unit vector in the same direction as another vector. We talked about that today briefly. Dot product, angle in between, projection vector, and the vector perpendicular to it. And then a unit vector parallel to a graph. Kind of like that problem that we did the other day. So those are the things. If you've been keeping up with your homework, those should not seem like daunting tasks. Okay, we've kind of just added a little bit each day. I know some of you may be thinking that these topics are very disconnected. Starting on Monday of next week, we will connect the parametric to the vectors. Okay, we will connect those 2 thoughts. All right, let me go ahead and stop this, and you can work